In this example, we're given a combinations of capacitors, resistors, and inductors connected in series parallel combination, and we're being asked to compute the equivalent impedance, meaning that they will be driven by sinusoidal sources. Okay, so let's get started. Well, I need to convert that one here, which is the capacitor. So we should remember that for a capacitor, what we do need is 1 j omega c. For an inductor is j omega l, and for a resistor is just simply resistor. Okay, so let's start off with this capacitor in here. So we're going to convert it. Well, it's going to be 1 divided by j. What is omega? Okay, so as it turns out to be that we don't have enough information to do these type of combinations because these capacitors and inductors, they'll act differently to sources with different frequencies. Okay, so we will have to be given also the frequency at which these sources are operational. Okay, so if I told you, let's start off by saying, well, omega for the first case maybe is 20 radians per second. Okay. Now we're talking, now we can actually compute things, okay? So now what we can do is j omega is 20, well, what's c? 1 times 10 to the negative 6, okay? So all you have to do is just multiply these, and you'll end up with the value that we're looking for. Well, this is not microfarad, this is millifarad. So before I do the computation, this should be negative 3 in here, okay? And if you do this computation, well, you'll end up with this particular value in here. Well, why don't I just draw it in here? I think it's just simpler, okay? So what we end up with is the following. So I'll draw the equation there, and the value is actually here. We'll get 50, or actually negative 50J, okay? That's what we end up with. And this is everything I'm going to convert to ohms, okay? What about the 100? The 100 stays the same, it's 100. How about the 8 henries? Well, the 8 henries is J omega, which is 20 rad per second times 8, okay? So 8 times 20 is just simply 160. So this is 160J. All right, what about the 200? The 200 stays the same, but what about the 1 millifarad? Okay, so 1 divided by j times 20 times 1 times 10 to the negative 3. Okay, so that's 1 divided by 20, negative 3 in here. What we get is very similar to the original one, which is actually we computed it here. I should have seen it. It's the same. Okay, it's negative 50J. All right, and I think now we have everything we need to compute the Z equivalent. So for the Z equivalent, what we have is these two can be combined now. Yes, it's an inductor and a resistor, but now we're dealing in the phasor domain. Everything is in phasor domain, so we can combine them. So what's the combination of these two elements in here? Well, I'll combine these two together, and I'll combine these two together now. Okay, so what we'll end up with is the Z equivalent here is 100 minus 50J. Okay, so that's an impedance and resistive component, and because the reactance, so the reactance in here is 50J, and because it's negative, it's capacitive. Okay, so we can do that in here, and this one here, we can keep it as a capacitor, but it's really negative 50J. And this one here now, what we have is the following. We have, this is 200 plus 160J. All right, so we're not done yet for the Z equivalent. So what we need to do is we need to combine these two in parallel, okay? So parallel wise, what we have is the following. We have 100 minus 50J, and then these two here combined in parallel, what we end up with is the following. You can basically, you can deal with it as Z1 and Z2. Let me just write it here on the side. What we have is negative 50J times 200 plus 160J divided by negative 50J plus 200 plus 160J. So I'll use my calculator to compute this. The answer happened to be here, 9.6, negative 55.28J. And now we can get that the Z equivalent of all of them, basically, this is the Z equivalent in here, is just simply adding both of them together. So I'll add 100 minus 50J to it. And what I'll end up with is 109.6, negative 105.28J. So I'm approximating here, and that's basically the Z equivalent that we see. This is for omega is 20 rads per second, okay? We can do the same type of analysis, but with a different frequency, just so that I'll do that very quickly just to show you what the combination, or actually you should be able to do it. It's the same type of procedure, but now the circuit, I'll just do the conversion for the circuit using the 20 rad or 10. Let's assume that here's what I'll do. So here's the circuit, and what I'll tell you now is I have omega now happen to be 10 radians per second versus 20 radians per second. So these values that we got in here, or the ones in here, they will not be the same. Okay, they will be slightly different. So how different will it be? Well, here. So the first one in here, this will be 1 divided by j. Omega is 10 times 10 times 1 times 10 to the negative 3. Okay, and that here is equal to negative 100J. Of course, this is negative 100J. I paid attention to it. The resistors stay the same. What about this one here? Well, this one will be J omega, which is 10 times 8. This is basically 80J. That's basically what it is. And you can see negative 100J and this is 160J versus 80J, negative 100, this is negative 50. So they're different. So the Z equivalent, if you combine them, you do the same thing. You combine these in series and then in parallel with this and then in series with that. And well, you'll end up with the Z equivalent at that particular rate is 149.5 negative 195.05 J. And as you can see, by comparing it to the other one in here, you will see that the Z equivalent here and the Z equivalent here are not exactly the same. So the Z equivalent, or the impedance that is seen by any source that's driving them, is different because it is dependent on the frequency. And in both cases, by the way, the negative here and the negative here implies that this here is capacitive. So if I'm to replace it, I'll be replacing it in both cases. Whatever it is, it will be a resistor for the 109 for the first case, and then 149 for the second case, and then a capacitor. And you can compute the value of the capacitor depending on the W. So what you do is you tell me 1J omega C, and this here, for example, is 105. Let me just write it in blue. So I'm saying, like, if you want to convert it back to the time domain to figure out what the capacitor that is seen by a source. So what you'll end up with is the following: 1J omega. Well, I know that omega is 20, and C is what I'm looking for. It just happened to be 1, or actually negative 105.28 J. Of course, this J with the negative and this J goes away, so that tells me, well, C is just simply 1 times, 20 times 105.28, and whatever the value you get, that's the value for the capacitor, or the equivalent capacitor in here.